Okay, I'd like to take this opportunity to talk about pKa's. And really, without mentioning pKa's, the discussion would be incomplete without talking about its complement, which is the Ka. Okay. So the Ka is a constant. It's actually an equilibrium constant, known specifically as the acid dissociation constant. Usually that is a constant that is quoted at 25 degrees C, and you look it up. So you usually look this up in a textbook. The Ka value just gives the propensity or the ability of an acid to give off its proton. So a Ka value, this A stands for acid, just is a number that tells you whose magnitude reflects how well, or the propensity of that acid to give off an H plus or a proton. H plus. Now, you may remember from your general chemistry class that H plus and H3O plus are essentially equivalent. H3O plus is called a hydromonium ion. And for purposes of this class, H plus and H3O plus are going to be used interchangeably. They're essentially synonymous. And really, I'm going to just say H plus from here on out. But that is a measure of acidity. So the acid dissociation constant is a number which is constant at temperature, specific temperature, usually at 25 degrees, that tells you how good of an acid that acid really is, how well that acid can give off that proton, if that proton is dissociable. So the best way to look at pKa's and Ka's, okay, one is really just a mathematical transformation of the other, but we usually like to go with pKa's because it's just easier to remember. You avoid all those messy exponents. But one way to really discuss this would be with some examples. So the first example I'd like to give you would be acetic acid. Acetic acid is our prototypical and classical weak acid. Okay, it's a carboxylic acid that has this structure. Okay. And that is the dissociable proton in acetic acid. So it reacts with water, and that reaction yields, now notice the arrows, so this reaction does not proceed to 100% product formation, hence why acetic acid is a weak acid. Hydrochloric acid or nitric acid or sulfuric acid, those are strong acids there. I mean, that arrow is going to go to the right. But acetic acid is a weak acid, but it can still have the ability to donate that proton and yield H3O plus, which I'm just going to call H plus, and its conjugate base. So the conjugate base of acetic acid is the acetate ion. So here is acetic acid. This would be a conjugate acid. To that conjugate acid, we have its conjugate base, which is the acetate ion. Conjugate base. So this reaction has an equilibrium value, or a Ka constant, and that value, which I look up in a textbook, is actually 1.74 times 10 to the minus 5. Okay, 1.74 times 10 to the minus 5. So that 10 to the minus 5 actually should clue you in on how well this reaction occurs. So 10 to the minus 5 is not very large. Okay, it's not greater than 1. So this reaction does not really go to 100% completion. Henceforth, it does not really produce 100% of H+. It does produce enough H+ to give acidity, but just not enough. So the Ka, like I said before, is just a number, and we look it up. It's temperature specific, so at 30 degrees it may be a little bit higher because higher temperature reactions occur a little bit more faster. But we usually quote it at a specific temperature, and usually the temperature is 25 degrees that we consult a textbook on. And that number just tells you how well the forward reaction goes in generating protons, or H+. So the Ka value is this. The pKa value, which is the jargon that we are going to familiarize ourselves with, is nothing more than the minus log of your Ka value. All right? So if you do that math, the pKa of acetic acid, this proton of acetic acid, will be nothing more than minus the log of 1.74 times 10 to the minus 5. And when you do that math in your calculator, you get a value of 4.76. Okay. So the pKa of acetic acid, that proton, is 4.76. Or you can say the Ka of that proton is 1.74 times 10 to the minus 5. Right? So that number just is a measure of acidity. Okay? The larger the Ka value, okay, the more the reaction favors to the right. These are equilibrium reactions. All right, so they proceed left and right. They don't go to 100% completion. Obviously, acetic acid won't go to 100% completion because it's a weak acid, and a Ka value of 10 to the minus 5 is pretty low. All right, so instead of saying 10 to the minus 5 or 10 to the minus 6, or some very, very weak acids have a Ka value into the 10 to the minus 12 realm, we just do the minus log of it. And by doing the minus log of that Ka constant, we get a nice number that we can reference it by. So it's just a mathematical transformation, minus log transformation to be specific, that gets rid of the messy exponent. So we can say 4.76 is the pKa of that proton, that dissociable proton in acetic acid. So you really have no way of comparison. 4.76 for acetic acid, is that a good acid? Is that a bad acid? Well, what's your reference? Okay, so usually you want to compare this to pKa's of other acids. So let's just take a look at another acid as our example. So let me, zoom back out of here and look at another example of this. Let's take a look at phosphoric acid. Phosphoric acid has this structure. Okay. It will react with water. It's the same equilibrium principle. And one of these three protons is given off by phosphoric acid and taken up by the water. And that's going to give you H plus, as before, and then the conjugate base of phosphoric acid, which is H2PO4 minus 2. Okay, this is phosphoric acid, your corresponding conjugate acid, and for your conjugate acid, you'll have the corresponding conjugate base, which is dihydrogen phosphate ion. So that's your conjugate base to this conjugate acid. So the Ka value associated with this at 25 degrees is 7.08 times 10 to the minus 3. Okay, 7.08 times 10 to the minus 3. I just looked it up in a textbook. So 7.08 times 10 to the minus 3, I can take the pKa of that, which is nothing more than minus the log of 7.08 times 10 to the minus 3. And when I do that math on my calculator, I get this value. So I'll get my calculator out here. Log 7.08 exponent minus 3. Don't forget I have to take the minus of that. And then take the minus of a minus is just plus. So 2.15, I'll just do that to 3 sig figs. 2.15 is the pKa of one of the protons in phosphoric acid. So one of the protons in phosphoric acid has a pKa of 2.15. Okay. Now let's just do a simple comparison here. All right. We had two examples of acids. We had acetic acid and then we have phosphoric acid. Okay. The Ka for acetic acid was, when we looked that up, was 1.74 times 10 to the minus 5. And then the Ka for phosphoric acid is 7.08 times 10 to the minus 3. Okay. So which reaction actually favors the production of H+? This is the question you should be asking yourself. A reaction whose equilibrium constant is at 10 to the minus 5, or a reaction whose equilibrium constant is 10 to the minus 3. Okay. What is Ka? Ka is the ability to give off that proton. We attach that quantitatively to a number that tells us how well that acid is in giving off a proton. Okay? So which would be the better acid? Okay? Well, 10 to the minus 3 is about 100 times greater than a number that's 10 to the minus 5. So we would expect this reaction to go more towards the right. And we would expect, comparing just acetic acid and phosphoric acid now, okay, comparing just these two acids in our example, we would expect phosphoric acid to be the stronger acid. So what is the pKa? The pKa is minus the log of 1.74 times 10 to the minus 5, which I believe was 4.76. And the pKa here was 2.15. All right. So what is the relationship between Ka and pKa and acidity? Okay, we already know this is a better acid because the magnitude of Ka is much larger than this. 10 to the minus 3 is much greater than 10 to the minus 5. When we do the minus the log transform, okay, it's a log transform, negative log transform to just get rid of that messy exponent. We get a number that's 2.15 for phosphoric acid and a number that's 4.76 for acetic acid. Right? So which is the better acid? Well, we've already established that phosphoric acid is the better acid compared to acetic acid. But what does that mean in terms of the Ka and the pKa? So what I'm trying to tell, hopefully you'll realize, is as the Ka goes up, you have a better acid. But also, just by the mathematical nature of the logarithm, the pKa value is down. Okay, so those are indicators of acidity. Okay, a large Ka value and a low pKa value. Okay, so Ka and pKa just tell you the same thing, how well a substance is as an acid, how well it's good as in behaving as an acid and giving off protons. But just due to the nature of the log transform, minus the log of Ka is your pKa. The lower the pKa magnitude, the lower the pKa number, corresponds to a larger Ka magnitude, a larger Ka number, and that just means your acid is more acidic. All right, so notice the inverse relationship. Strength of acid means a higher Ka value, but a lower pKa value because of the mathematics involved in the logarithmic transform. So how does this deal with biochemistry, Kas, pKas? Well, like I told you before, earlier on, we generally like to talk about molecules in terms of their pKas. And amino acids have a pKa value. Okay, so in your flashcards, you actually denoted all the pKa values of all the ionizable protons. Alpha amino goes off at roughly 9. The alpha carboxylic acid proton goes off at roughly 2. Some side chains go off. So let me just give you one example of an amino acid, give you their reactions, and then your Ka values, and hopefully you'll know what pKa is, because really these are just cousins. Okay, cousins related by the logarithmic mathematical function. So let's pick any amino acid now. So what amino acid shall we pick? Let's see here. off the top of my head, I'll just pick, how about the amino acid tyrosine? Okay. So instead of thinking about Ka and pKa's with acetic acid or phosphoric acid or hydrochloric acid and all those acids, think about Ka's now in terms of biological molecules, amino acids. So tyrosine has an alpha amino group, an alpha carbon with an alpha hydrogen, and an alpha carboxylic acid group, and a side chain. So the side chain of tyrosine actually has a third ionizable proton. Okay? So what are the ionizable protons in tyrosine, this specific amino acid? This proton comes off, one of these protons comes off, and then yes, a third proton comes off. So what are the reactions for this? So this proton, remember the alpha carboxylic acid proton comes off at roughly around pKa of 2. So let me quote the specific values here. This amino acid, tyrosine, will react with water and will give you NH3 plus with its alpha carbon, alpha hydrogen, COO minus. The proton is gone. Okay? And then our side chain is here. Alright, so this proton is gone. And you will also get H plus, or H3O plus. So what is the Ka for this value? All right, the Ka for this value, if you look it up, is going to be around 6.31 times 10 to the minus 3. Okay, so we don't memorize Ka's and we don't memorize pKa's. Okay, there's no reason to memorize it. Okay. Because these are values that you just look up in a textbook. So when I found the Ka for this reaction, I did the minus log of that to get the pKa, and then doing that math, I got 2.20. Right? So the pKa for this proton is going to be 2.20. Now, what about this proton and this proton? All right. So again, you're going to have to know when these protons come off. Now, you don't need to know the specific Ka constant or the pKa constant. That should be in your flashcards. Okay, your pKa should be in your flashcards. All right. What about this proton here? All right. The reaction for this proton is going to be this. This proton has already come off now. And it's going to react with water. And now this proton is going to come off. The alpha amino group begins to donate its proton. And you'll get this structure here, an NH2 alpha carbon COO minus. The side chain remains the same. Then we have an H plus here. So what is the Ka for this? When I looked it up in the textbook, the Ka for this is 6.17 times 10 to the minus 10. Okay, so this proton has a Ka value of 6.17 times 10 to the minus 10. And then this proton in the first reaction has a Ka of 6.31 times 10 to the minus 3. Okay, so yeah, okay, this proton comes off at a pKa of 2.20. All right, let's do the pKa for this. The pKa is minus the log of the Ka value, 6.17 times 10 to the minus 10. And when you do that math, you'll get a pKa of about 9.21. Okay, so the alpha amino group for tyrosine has a pKa of about 9.21. Right. Yet there is a third proton that comes off. Okay, so let's take a look at that third proton that comes off here with the side chain. And that's going to look like this. Oops. Okay, this proton came off. The alpha carbon. The alpha carboxylic acid came off. This has an ionizable proton. This proton has a pKa. So what is that reaction? Right, this proton comes off. Here we have an NH2. We have a CH, COO minus. And then our side chain is CH2, O minus. Okay, and of course we'll get H plus. What has happened here is that this proton has come in and protonated that water molecule. So is this reaction really favored? Well, if you look up the Ka value for this, it's 3.17 times 10 to the minus 11. 3.17 times 10 to the minus 11. Okay, something that has a Ka value of 3.17 times 10 to the minus 11, is that favored? Okay, 10 to the minus 11 is very, very small. Okay, so probably not favored, but it will happen. Okay, just it will happen very, very rarely because, again, the Ka for this equilibrium reaction is at 10 to the minus 11. So the pKa is minus the log of 3.17 times 10 to the minus 11. And when you do that math, I got 10.46. Okay. So the pKa of this proton is at 10.46. So that is the relationship between Kas and pKas. It's minus the log relationship. One thing in terms of math, so just be aware. Let's go here. Okay, pKa is minus the log of your Ka, equilibrium constant. All right, so we can go back and forth between the two. Okay, to get the pKa, we take minus the log of Ka. To get the Ka, we have to do this. Ka is equal to 10 to the power of minus pKa. Okay, so this is the inverse log relationship. So if you go to your calculator, you have the inverse log function. Okay, so if I take the inverse log of 10 to the power of minus 10.46, I get 3.46 times 10 to the minus 11. So that would be my Ka value. Okay. So if you want to go from Ka to pKa, okay, you have to do 10 to the minus pKa. If you want to go from Ka to pKa, 10 to the minus pKa gives you the Ka. If you want to go for pKa, from Ka minus the log of Ka gives you the pKa. So just understand those relationships. Okay, this is just math, so it's just math, and then realize also that pKa and Ka are measurements of acidity. They're numbers that we attach to a specific acid. In this case, we can attach it to an amino acid that tells you how well that amino acid is in terms of its propensity to give off a proton. All right, so that is our discussion, a short discussion on Ka and pKas, where they come from. the reaction that describes a Ka, and what a pKa actually is. It's just measurements, they're just indicators of how well on a molecule, and now we're talking about biological molecules, amino acids, yield a proton to water. All right. So in our next discussion, we'll talk about how to solve isoelectric points of proteins. We'll also talk about peptide bonds joining amino acids together. Thank you.